Welcome to this session of Shadow the Scientist. My name is Jamaica Marshall, and I am your Shadow the Scientist Programs Manager. As you can see, I am live with Bryce Bolin, Laura-May Abron, and we have two guests here. Leo, please introduce yourself.
Howdy, I'm Leo. I'm the staff astronomer for tonight. I'm one of the instrument scientists who supports MOSFIRE.
Yes, yes, yes. So she was helping us get the calibrations done, helping Bryce and Laura May get their calibrations done earlier. And I was observing this incredible process. It was great. We got some great footage that I can share later as she was explaining things. And we also have with us from the software team, Miss Ava. Would you like to introduce yourself?
Hi, my name is Ava. I do software here at Keck, and I'm learning about more of the observing process.
Yay. So as you can see, we have a very full, very full control room here and control room one. We are in the base facility for CAC, and this is in Waimea, just the northern part of the Big Island of Hawaii. I'm so glad to see all of you here. Annalise, welcome. So glad to see you again. Barton, Bill, thank you for the compliments. Bill said my earrings were really pretty.
Nice. They are
Thank
very
you.
beautiful.
Thank you, Bill. These are my favorite earrings. JC, welcome, JC. Karen, Lawrence, hello, Mark. Nade, my friend. So glad to have you, Nade. Rob, always a pleasure to have you. Vonnie, hi, Vonnie. And Miss Yuli, hi, Miss Yuli. As you know, we're looking at three different types of objects. Neptunian Trojans, hopefully also our third interstellar visitor, 3I Atlas, and also some Earth co-orbitals. So we will discuss this in the chat. All right. Thank you all for being here. Questions, comments in the chat at any time. And I'm just going to be right over here.
Motion.
This is the here, and here. Those are those guys.
Yep, I recognize that pattern.
It changes so often as blanket in between exposures.
Yes, everyone, feel free to introduce yourself in the chat. Tell us where you're joining from.
Okay, so we might just have to do this post-processing. Just trust that it's there.
Yes, Miss Yuli, thank you. So we have a request. We have a sixth grader with us. So,
Hey,
so any explanations you can do would be appreciated.
hi there.
Thank you, Miss Yuli. They're on it.
Should explain why we're dithering.
Yes. Let's see. So I just saw it there.
Well, what dithering even is.
So you see what this is what I keep seeing. What is going on there? See how it's like
It looks like there could be
I
some
got you, Miss Yuli. Thank you.
saturation possibly of some targets.
but it's
Doesn't look like saturation though.
But when it shows the side, it goes away. Science image, it goes away. And then when you do the science image difference, it looks like it cleans up pretty well.
Yeah.
So I think it's like some kind of process.
Must be.
So to everyone, you also see pinned in your window Heather Hershey. Now, she's on the phone. She is at the summit of Maunakea at Keck at the telescope, and she is running the telescope. So you get to see her. She'll come on when she has time, but clearly right now she's a little bit busy. So we have the full Keck team here this evening, you all. So all your questions, please post them here.
Yeah, so one go out and three.
Yeah, you went.
Bill from Not Dark Sacramento. Okay. Welcome, Bill. So glad to have you.
Cool. I didn't realize you were looking at the mosaic. That makes sense
Yeah, that
now.
makes sense.
Should I box 5 again?
I think I did see the asteroid in there.
Well,
wait
wait
for it
for
to
the
stop
yeah,
moving
to
and all
stop,
that.
I think.
Yeah.
Because you can't do wait and go in this little thing.
Yeah, sure.
But we have to use it because it's what worked with those. It's what works on Sidereal. Yeah, sorry, we're like troubleshooting some stuff here. We think we got it, but are y'all watching y'all are watching on screen here. So in the bottom left hand, so we have 4 panels here. We have 4 different screens going on.
You ever wish for touch screens?
Okay,
No.
all right. So wait for the pupil. It says open.
Yep, okay.
Yep.
Gotta wait for it to say tracking, or is open okay?
Yeah, open's good.
Okay, so let's go.
You only need it to be tracking in K-band.
K-band. Oh, pupil needs to be tracking in K-band.
Yep.
That's a new thing I've learned. Okay. Pupil.
Everything else, it can just be open.
Ah, okay.
Hello, I see Nade, you're joining us from Hilo. Yes, welcome Nade. Vani, you're viewing from Happy Hilo, Hawaii. Yes, looking forward to this amazing session. Absolutely, Miss
Hello.
Vani.
Hi, Vonnie. So, okay.
And Rob from LA. Hi, Rob.
So this is the first one.
Rob, the next time you're in town, let me know so you can join us live in one of these sessions, okay? Any of you guys in town, let me know.
So yeah, so we have 4 panels here. In the top left panel, that is the instrument controls. That's where we control the camera and we tell how long it to expose and when to expose. And on the bottom left-hand panel there, that is the images that we're seeing coming in. And that's what we're doing. We're troubleshooting that to make sure the camera's working, because we just started not too long ago. We just focused the telescope and we're now taking data of our first target. So we just want to make sure that the data are looking good, the camera's looking good. And so far it looks like it's going well. We got a 0.4 arc-second seeing, which is really nice. And the other 2 panels on the right-hand side, the top right-hand panel, we're not really using that tonight, but that's to control the configurable slit unit, because this is a spectrograph,
Yeah.
but we're using it as an imager. So we're not using that right now. But in the bottom right-hand corner, that is something that we're using. This is our telescope control. We use this to control the telescope itself. So you actually have multiple different machines, one for controlling the camera and one for controlling the telescope. You want them to be set on separate computers going at the same time.
Excellent.
So it looks like we just took, let's see, 80. I think we just took 1 Y image so far. Check here. 86 minus 85.
That's not it.
I'm thinking that might be it
I
because
saw it earlier and it had a similar shape.
but there is a source. So if I'm looking at number 40, frame 40, the position of the target for 540 UTC.
Oh, you're right.
Yeah,
There's a
we
source
moved
there.
out of
Yeah,
that.
no,
So,
that's the source.
so now we just got frame 87. 87 minus 86. And we're going to zoom out a little bit here. I'm checking my source image. So the ephemera says that it's somewhere around here in this vicinity. Oh, I just got another exposure, so it resets the entire thing. So I have like 30 seconds to check. But that's the way it goes. So it's saying it's somewhere around in this vicinity. I don't really see it. It's pretty, I guess it's pretty faint.
So for people watching, we're trying to find the asteroid
Yeah.
in our image right now, and they're much fainter than the stars. So
Okay, well, I think we can move on to our next target after this.
Okay.
So are we done? I think we are done.
I think we are done.
So the next target that
Don't
we are
forget to go dark.
Oh yes, so we
Quick
click
dark?
on click on this, click on quick dark. So the next target is going to be 2015 VU207, and you want to click on the date that is I think we're in 30-minute intervals here.
Yeah.
So you want to click on 5:30, the closest one.
You all, the targets are in the
Is that
bottom
5:30?
right,
Okay, very good.
that bottom right
And ask
window.
Heather to slew the telescope.
Heather, if we could slew the telescope, please.
Yeah, so Laura-May highlighted the
Just
target,
selected the target.
and she highlighted it, so it should be good to go.
Okay, can you guys hear me on here? You guys hear me on the Zoom?
Guess my Zoom mic is not working.
What's that?
Hold on. I guess my mic on Zoom is that's not
Oh.
working. So, but I'm still in.
Fiber are trajectory destination magic seat limit.
I like watching slew on.
Yeah.
It's fun
We do have 2 questions if you have time.
on the Zoom.
Yes, we do. First question is from Bill. Does most of the research get done from Waimea,
Yes.
from here?
Yes, we are taking the out. Yes.
The data collection is done here. Yeah. So this is the fundamental. Everything comes from the scopes here. I mean, not everything in the world, but
But this,
and this is the best sky in the world. Even better than Chile, the conditions are here. So
thank you, everyone. And second, Mark asked, and this is Mark from Fair Oaks, California. Welcome, Mark. The question is, what kind of scope is being used here?
ooh,
So it's a 10-meter telescope, but please continue. We can talk
Bryce,
about
you
the
know more
instrument.
about the tech.
So
A reflecting telescope.
yes, it's a reflecting telescope with an aperture size of about 10 meters and an F ratio of about 1.4 at the prime focus. We're using an instrument called MOSFIRE, which is attached to the Cassegrain focus of the telescope, which is a F ratio of about 15. And this is an infrared instrument. It is a spectrograph and an imager with a field of view of about 7 arc minutes in diameter. And tonight we are using it as an imager in imaging mode.
Brilliant.
Also, the mirrors are, for anyone who's familiar with the James Webb, for example, that has that kind of cool honeycomb structure. I believe that was somewhat inspired by Keck. I mean, it's obviously there are other.
Have we arrived at our target, Heather?
I think we're still slewing.
Yeah, we're still slowing.
Yes, it looks like we're still slewing.
Okay.
And so the mirrors
we're
on the
currently
Keck
still
are
slewing.
also.
I'm sorry, what was that, Heather?
We're currently still slowing.
Okay.
So the mirrors on the Keck are also these segmented mirrors. It's very, very beautiful.
Mhm.
Very beautiful mirror. Yeah,
Yes,
but it's
it
not one
is.
single piece.
Yes, it's not one single
Because
piece.
the limit of those is I think 8 meters, 8 to 9 meters for a single mirror.
Ah.
Your limit is kind of like 8.1 meter, 8.5. I think Gemini and a couple others are basically as large as you can get them.
And so, so it's not optical. They're looking in the infrared. That's right. That's right. Yes, Mark.
Does Mark have a question?
Oh, Mark was just clarifying. So you're not looking. It's not optical, and so
No, it's
no,
infrared.
it's infrared.
And that is a big important point, because the way that we take images is we take images in groups of 5 or 9. And we do that in order to create a special map that allows us to subtract the heat, the emission, the light, because we're in the infrared. Heat creates a source of light, creates a background in the images. And so we're taking images in groups of 5 so that we can subtract the emission, the contribution to the background in the images, which is caused by the heat of the instrument and heat of the sky as well. In optical, you don't have to deal with that. You just take one image. But in infrared, you take groups of 5 images or so.
Thank you, Bryce. Thank you, Laura-May. Thank you, Leo. Thank you, Eva.
It's really we're looking at the sky cameras out here, and it's very very pretty.
It is gorgeous. I will drop a link to the sky cams in the chat just now.
It's pretty amazing to think that I think a lot of us are used to very light polluted skies. And so we don't usually see, at this time, an hour and a half or so after sunset, to see such an incredible starry sky.
It is so beautiful.
Drop that link in the chat. And Laura-May, our targets right now we're looking at are the Neptunian Trojan. No.
What is this one, Bryce? I think that's just, is it another main belt?
This is a Neptunian Trojan.
Oh, this isn't Neptunian
Yeah,
Trojan.
the current one.
Neptunian Trojan. Yes.
BU 207.
Question. Okay. Welcome, Abel from Cusco, Peru. We're so happy to have you, Abel from Peru.
Hello.
Hola.
Yes.
Or
Hola.
buenas noches. I guess it's,
We have-
what time is it in Peru right now? It can't be, it's gotta be less, it's gotta be what, 2-3 hours, oh no, it might be 4 hours.
But still
Or
nighttime.
it's
Yeah.
almost nighttime.
We have so Jamaica is fluent in Spanish.
Ooh.
Yes. But now I'm feeling slightly put on the spot and I'm gonna mess up all the things. So thank you. Yes, Abel. Yes, Abel.
Say the full oh, go ahead.
Just congrats.
And
And we'll get to your question as soon as they have time to answer it, Abel. Thank you.
okay, so it looks like we're getting to it. Cool. We got a big heavy telescope here.
Takes a while to slew. Yeah.
Oh, do you have time for a question?
Sure.
Okay, so Abel asks, what noise reduction algorithm are you applying to the calibration frames, considering you're operating in the infrared?
So what we do is we take data in groups of 5 or 9, and what we do is we create a mask, like a mask of the emission by combining those images together, and we remove all the stars, remove all the asteroids from that. So you just get a smooth image that the sky background counts are in, but nothing else. So when you go back and you go into the individual science images that have the asteroids and the stars in them, you can use that sky background mask to remove the sky emission from the individual science images.
I hope that was
So
a good answer.
we have a quick version of that here. So this is like a quick look way of looking at that. But if I look at the image auto display here in the bottom left hand corner, and I press the tab button, you can see that there is white stars and black stars, and so that's because I'm subtracting the images from each other. So where the values are negative, that's where it's black, and where it's white, that's where the value is positive. So you're subtracting 2 images from each other. So where the star was in the image before, it's a negative value, so it appears as a black spot. And where it was currently, that's where it's positive, and you get that white spot. Now the idea is that you subtracted out the sky and the instrument contribution there to the background. So you can see the images, you can see in the image, you can see the faint sources pop out a lot. So I'll show you before. Oh, that's the mosaic. This is the before version. You can see it's kind of hard to see the stars. And then I press tab, and here's the after version. Things are popping out a lot more. You can see a lot more stars. Yeah, I'll zoom out a little bit more. Zooming out a little bit more shows it a little bit better. So I'll show the before. Okay, I think we might be done slewing.
Awesome.
Stars, something went really far.
You're welcome, Abel.
So we want to get this ready for the next one. So type it here. Or are you doing a pointing check?
Yeah, just a quick pointing check.
Cool, thank you so much. So Laura,
Wanna make sure.
you want to get it ready?
Yep.
So it's 2015. So you want to change the object to 2015. BU underscore BU 27. No, 27.
27?
No, sorry, 207. No, you're right.
That's what I said.
207. Yeah, 207 is fine. Yeah, that's correct. Cool. Okay, so we 30.
We're gonna be in
we're
Y?
gonna be- We'll wait because it's
Oh,
still
okay.
she's still slewing. So we
So
want to
be
30 seconds. 30 seconds in one
then
go
go
ahead.
ahead.
Yeah.
Box 5?
Don't worry about that because we'll run
Okay.
box 9 in there. Actually, for this one, these are pretty faint. Can we do like 180 seconds in wideband?
180 seconds. I mean, you guys can do what you want.
You don't think it'll saturate or anything? 180 seconds.
I have no idea how bright this target is.
It's
so.
pretty faint. This is a 22.3.
I would recommend not doing box dither pattern and try doing a sample exposure then just to make sure. So
Okay,
just a stare.
So stare. So we're good. So we're gonna do.
We're good here.
Did you want me to leave it at red?
Mm,
Leo?
if let's see.
I think it's gonna be really off video.
Yeah, put it in MOSFIRE.
Can I go to Y?
Yes,
Not yet.
please go to Y.
Okay, great.
So let's do 180 seconds. Let's try that out.
Okay, you're set up.
All right.
All right, let's go. We're good.
You're
Wait,
still in
No, wait,
apply.
still, yeah. You want to do you
Wait
want to
to
do
go.
wait.
Yeah,
go.
we can go for this one.
Yeah, so it's going to start. It's going to wait before it's done.
You know, the subtraction kind of reminded me of in Photoshop. Sometimes I remember in the past seeing a tutorial where you take a picture of, I don't know, the pyramids in Egypt, and there's all these people. But if you add all your pictures that have all the people in different places, then you can remove everything except your beautiful pyramids.
Oh my goodness. Oh my goodness. The pyramids of Giza.
Yeah.
Okay, yes, Mark, thank you. Is it possible to increase the size of the shared screen because it's hard to read? I don't think that we can.
There might be settings on his end. I'm sure you can zoom in on what you have on screen, perhaps.
That's right. Thank you, Laura-May. Yes. So I'm sorry, who was that? Yeah, Mark, can you try zooming in for me because I can't really change this setup now. I apologize. Thank you. Yeah. And I can't zoom in. I was just trying to do that for you, Mark, but I'm not able to on my end. Sorry about that.
We did 180 on the iTime.
That's right.
So you're doing a longer exposure because it's.
Oh yes. This is something out by the orbit of Neptune. What we were observing before was in the inner main belt.
Oh.
That's right.
We're not in box 5.
We're going to do box 9s because for these faint sources, I've learned that you really want as many dithers as possible for background removal.
So, question, what is our specific exposure time per frame, and what is the total integration window needed to confirm the TNO's proper motion against the infrared background?
Yeah, so the TNOs move very, very slowly. This one moves about 0.06 arc seconds per minute. So that means at a 3-second exposure, it's going to be moving just maybe 0.2 arc seconds. It's very, very slow. So it's going to appear as stationary. Now, the way you get around that is you find the object, and even though you can't really see it move, you can measure its position in the sky, and you can fit an orbit to it, and that should check. That is like your check. Okay, so we got 42,000.
Yeah.
Ooh, it's the end of the line. All right, so yeah,
You can tell the exposure's all blown out.
we want to do 60 seconds.
Yeah.
We want to do 60 seconds. 60 seconds here. Wait and go. We'll do a test. Since 30 seconds is the recommended time.
Yeah.
So we're really pushing it. We were really pushing it. It didn't like it. See if we can summon the kitty cat. So we have a cat here. So I'm gonna.
What's the name of the cat?
Yeah, what is the name of the cat?
I don't know, but if we open the window here a little bit, we'll hear our voices.
Are you sure it's a friendly cat that way?
Yeah, it's a scaredy cat. But if you are calm, she'll come and sit on that table right there and stare at you.
Sure.
Yes.
So I just dropped in the chat a link to Asahi Astro Live. This is a camera. It's live from the Subaru telescope, and you can see the summit, and you can actually see Keck 1 is open. That's us. That's us. Keck 1 is open, and it's a gorgeous, beautiful, beautiful sky. Take a look at that. Oh, Heather uses this to look for fog in the east. Yes, Heather.
Trying to approach the nonlinear. So I would say, like, it's a really nice image, but we're starting to approach the nonlinear. So I think, yeah, maybe we just stay with 30 seconds.
30 seconds.
Yeah, so let's be safe. So we'll do 30 seconds, but we do want 180 second. So it's going to be 6 coads.
Excellent.
And this will be a box 5. I think it's
So I was noticing your dithers aren't quite right. Can we try doing it on the exposure control? I just want to see what happens.
okay. So I'm going to go to box 9. There we go.
Thank you.
How does that look?
That looks good to me.
I'm going to go to apply.
All right.
So do you think we can do box 9 in here?
Give it a try.
Yeah. So this will take about 30 minutes.
Oh, wow. So there's RI offset 0, deck offset 0. Okay, actually that should be.
So this is the first position. So maybe it's not.
Yeah, maybe it's not. I'm gonna keep an eye on it for the next one.
Okay.
Tell me if it doesn't dither.
Ooh, yeah, we definitely want to do it.
This one's 30 minutes, you said.
That's right.
Where were those cupcakes?
Oh, thank you for sharing that, Rob. That's great. Yes, hopefully that'll work. Thank you so much, Rob. Mark, let me know if that's better. We do have another question.
Sure.
Ready? From Miss Vani. What is unique about the targets that were chosen, and what data do you hope to acquire?
So these are asteroids that are out by the orbit of Neptune. And the data that we hope to acquire are near-infrared photometry. So we're taking images of these faraway objects that is beyond the visual range of our eyes. Our eyes can see violet light, which is around 350 nanometers, 350 nanometers, out to very, very red light, which is about 800 nanometers. We're looking at light that is at 1000 nanometers all the way out to 2000 nanometers. So more than twice of what wavelength ranges that the human eye can see. But the reason why you want to look at asteroids in this wavelength range is because this area is very diagnostic. It tells us about the surface properties of these asteroids, what kind of ices are on these objects. If they are methane rich, ethanol rich, carbon dioxide ice rich, water ice rich, we can get an idea of what the surface materials are like on these objects, what surface ices these objects possess. Does that help?
Vani, let us know if you have a follow-up to that. Thank you. Thank you,
Yeah,
Bryce.
no
Thank you
worries.
so much. And we do have a follow-up from Abel. Do you confuse TNOs and faint stars sometimes?
Oh yeah, that's a very good question. Yeah, so that's why you do the orbit fit, because if you're looking for near Earth objects or main belt objects, those objects are moving about 2 arcseconds a minute to maybe 10 arcseconds a minute if they're really close by. So from image to image, you can see them move very quickly. But for TNOs, it can take hours before you see them move. So what you do, and on top of it, they can be near some other kind of star where you're not sure. Because if it were a moving object, you could see the object move relative to stars. So it's easy to test whether or not that's an asteroid or a star. But because these things move so close, if there happens to be a background star nearby, you can get a little bit confused.
I'm going to abort after frame because you did not.
It didn't dither.
No.
So the box 9 script is not working.
This box 9 script is working. I think I have a hankering of Y. So I'm gonna see if I can abort after frame.
Okay. Thank you.
Thank you, Leo.
Thank you.
Is it something mechanical or a software?
I think it's a software issue.
Oh. So should we try and use the exposure control GUI instead of the
If you wouldn't mind trying, that would be lovely.
Okay, because I remember like this was like eons ago, and I have it in my notes saying, "Oh, use the box 9 thing."
It
But-
thinks that the node is set to 0 on
Okay.
that. So I might need to try it on the exposure control, and if that doesn't work, then I'm gonna try setting it by a keyword.
Yeah, I think that checks out because I remember I had to set nod E and nod N,
Yes,
so it just doesn't know.
yes. So you had to set those previously?
Yes.
Okay, so that explains it.
Okie dokie.
So I can set those for you if you would. Like.
Sure. That would
Okay,
be
I'm gonna
great.
wait until this reads out.
Thank you so much.
How could you tell it wasn't dither?
You can see on the offset on Faxum that the offset is 0 when it should be something.
Mm.
What did you set them to previously, Bryce?
20.
Okay, thank you.
All right, so I had that in my notes. So you have to do this now.
So I'll set that, and then you can try doing box 9 on the command line again.
Yay! Thank you so much. Yeah, thank you for catching that, Leo. This is why it makes me scared to not have you here.
We need you, Leo.
Yeah, I know, because it's like scary. Because tomorrow you won't be here.
Yeah,
We have Sherry.
will be here.
Sherry.
And Sherry's been on here longer than I have. She helped me when I was an observer here.
Oh wow! So she really knows it very
Yes,
well.
she does.
Perfect. All right. The kung fu masters of the instruments pass down their knowledge to future generations.
Yes.
So yes, we have about 10 seconds.
Okay, then I'll set those.
Abel, could you clarify that question for me? I'm sorry. How do you deal with what? Thank you.
Oh, okay. It still is trying to go.
So you gotta like control C it.
Yeah, that's what I'm doing.
Perfect. And then you and then I guess
All right, I'm gonna set abort.
okay. So we had a nodding telescope.
Not listening.
Can you explain nod for us?
So the nod. So you, when I was describing before that we have to remove the sky and instrument background from the images. So the way you do that is you dither. You instead of taking the image in the same position over and over again, you dither a little bit to move the stars and the asteroids out of the same positions where they are in the previous image, so that in the next image they're at a different position. And you do this 5 or 9 times, so that you can combine the image with a special technique that removes all the asteroids and stars, and you just get this smooth background. That's the heat from the sky and from the instrument. And then you can subtract that from the science images so that they have a background free image. And the nod is the distance that you tell
Alright.
the telescope to move in between exposures. So now, yeah, I think it's listening now.
Yep.
Well,
I aborted it.
thank,
Hard aborted it.
thank you so much.
All right. Plus 20. Yes, not there. Mod E equals 20. Okay, so are we back at 0? Great, great, great. All right. That should be okay. Excellent. All right, I think that you can try again with box 9.
All right.
All right. Oh, do we do is nod E A N and nod E set up?
Yes,
Okay.
I just set them up. If you would like me to confirm with you, I totally can. I
Oh
will
no,
show
that's
you
fine. We trust you.
here.
Do you want to type
Yep.
in box 9? Thank you, Leo. Laura-May, do you want to get the box 9 going?
Sorry, I didn't notice that earlier, y'all.
No, that was great.
Thank you. Back to your previous target.
We're still on 30 eye time and
Yeah, that's fine.
good to go.
Yeah, it's good to go. I think it should be fine because the previous target was moving quickly enough that you could use the further spaced images, and it's a bright object. So I think it was just self-subtracting itself.
Okay.
And so when Jen reduces the data, he just has to know
Okay.
process those images in a different way. Actually, I think he's probably going to make me do the image processing. So I just so I'll just have to
Do you normally have-
check our notes and process them in a special way.
do you normally process your own data or do you hand it off?
Well, it depends. So for imaging, I do the processing myself, but for the spectroscopy, Leo and Max have a special softwares for doing that.
Yep. But I don't know much about imaging. I know how to get you data on imaging. I don't know how to use it.
Yeah.
Have you tried, is it, again?
It looks like it's going.
All right.
Going.
Chugging along.
It's a pretty little galaxy.
Yeah.
Oh, in the bottom right, yes, in the viewer, that is a lovely little galaxy. That is.
Spiral.
Yeah, there do be a lot of galaxies out there. Yeah, you can see it right there. In the,
Yeah. Oh, yeah. Oh, that is nice.
Can you point that out? Sorry.
You sure it's the same one? It looks a little further down. like the
well,
algorithm
so
of the-
it's
Oh, I see it, yeah.
Yeah, that's nice. Oh, and then yes, it's flipped. Okay, yeah.
yeah,
That's right.
I think it might be a different screen. Yeah, no, you're
'cause
right.
There's
yeah.
the two here that are not,
Maybe it is different,
that seems closer.
but you see, yeah, maybe it's like
I'm
that.
just gonna keep an eye on this for you to make sure it actually does.
Yeah. So north
Did
is
it
up and
correctly.
north is to the right and east
Yeah.
is down. So it's kind of like that.
Ah.
So it's kind of like that. It's kind of the orientation we see it at right now.
What catalog are you using on the web?
I use Pan-Stars.
Yeah, that's right.
The best one ever.
I think you might be biased.
Slightly, just slightly.
No pun
It
intended.
is the current best
Ah.
one.
Oh, that was good.
So it is the current best one out there. Deep Sky Survey can be pretty good, but Pan-Stars has better resolution, so it really helps.
There.
But Ruben is supposed to make a new one in
Yeah.
like 4 or 5 years. We'll have a really good one, and
Great.
then we'll replace all this. But until then, Pan-Stars is the way to go.
Mhm. You were talking about Aladdin earlier being a tool that no astronomer should be without.
Yeah.
Right?
There's 2 tools that I like a lot. One is Aladdin, and the other one is UTC time. So UTC time is a little clock that sits at the top of your toolbar that tells you the UT time, universal time. And that is useful because all the coordinates are given in UT time for asteroids.
Okay,
when you
we're together.
Oh, great. Thank you so much.
Yay.
Woohoo.
Nice.
So let's see if we can play Spot the Asteroid here. It's going to be very difficult because we don't have,
That's
I don't think we have the image ready yet, but see, you can see the galaxy here. The galaxy is right there. And that star is right there.
Yeah. Right.
And so the asteroid is going to be somewhere here, there in this blank portion of the sky, which is great. We don't want any, stuff there. We don't want a TNO there. We don't want background stars near our TNO. So it's not looking. So that's the problem. Is when I'm looking at DS9 Aladdin, the limiting magnitude of pan stars is like 23rd magnitude. But if I'm looking at objects that are like faint 24th, 25th magnitude, you're going to see stars that aren't in the catalogs.
Yeah.
So that's why we need Rubin Observatory, because it's going to see things down to well past 25th magnitude. So we just got to wait for them to get their survey going, get it ongoing. It's probably going to take a year or two for it to really spool up. Pan stars took 2 or 3 years to really commit to iron out all the kinks before it really started taking the science data. But this is the way surveys go. This is why I recommend to grad students, don't ever do your thesis project on telescope or instrument that isn't already on sky and taking data for at least 4 or 5 years. If you're like the postdoc or the grad student that gets hired, oh, we're building this telescope. And by the time you arrive and you get started here, it should be on sky and taking data. Nope. I knew many a grad student who were hired thinking that they were going to do their thesis on pan-STARRS data. But they were like already done with their PhD by the time pan-STARRS actually was on sky taking data. So they had to do their PhD on something else.
That's rough. Okay, so for all of you grad students out there in the chat, I know there's at least one grad student in the chat. I won't call their name.
If
but
you are an undergrad and you're looking for like an undergrad project, or you're like a master's student and you're looking for like a master's project, only do your projects on data where the data are already available in an archive somewhere. And the data are good, well calibrated, and there's no issues. Don't ever have to rely on taking new data. Because you also run, even with a telescope that's perfectly running and amazing like Keck, if you run into weather problems, it could delay your graduation date, because it means you got to come back the next semester, and give it another go. And if you're like me, you had really bad luck. You could there was one year where not on Keck but on a different telescope when I was at a previous institute. There was one telescope I was trying to use where one year I think I had one good night out of 6. The rest are just weathered out. And so if you are, I was already a postdoc, right? So this was kind of side project for me. But if you're a PhD student and you need those data for your thesis, you're in a lot of trouble.
Yes. So the PhD student who I was thinking about has responded. I didn't want to call them out, but she did.
It's got the data. Here we go. Super deep image. Let's check it out.
Let's look at the data.
Ooh, it's beautiful.
Oh, wow.
So
Nice.
so we just use that technique, the sky removal technique. Now we only have 2 images here, so that's why you see the residuals, the negative residuals in black. But when you have 9 images, you can bind them in a way that you don't have any residuals. So here's the galaxy right there. This is the galaxy we're talking about. So I'm going to use a special technique right here called min-max to really change it so we can see the spirals.
Oh, yeah.
I zoom in here, and then now I'm going to change make it log scale. See, it's a little bit difficult because in infrared you have such a wide range. So I'm going to do min-max, linear, scale, scale parameters, and I'm going to do kind of a customized thing here on the job. So this is Uncle Bryce's word of caution for grad students.
Yeah, she did. She said thank you for that advice.
It doesn't let me change it. Okay, all right. So let's see if I can do something else. Oh yes, many a grad students runs into issues as a result of. You can kind of see the spirals, but yeah, because it's pretty. Yeah, so I can get the min-max going, but I can't reduce the contribution from the less bright pixels. So let's see if I can do scale here. Well, yeah, you can kind of see the spirals there, but I'm using Z-scale right now. So let's go look for the asteroid now. All right, so I see this thing here, and so we have So okay, I think I see it actually. Wow, so this is the power of the MOSFIRE. So we have this thing right here, right here. This might be it, actually. That might be it. Because this makes like an elbow. So it goes like that. That
Oh.
might be it right there. Yeah.
Oh, wow.
So that's pretty good.
Or is that the galaxy here?
No,
No,
this
that's a different one, right?
the galaxy is right
Oh,
here.
that's right.
That's the galaxy. And that is the
That little asterism.
yeah. So this is a brighter one. I chose a brighter one first just to like test out. Thing. But these are, let's do a signal check here. The signal is pretty good. There we go. So that's the 180-second exposure is. Yeah.
Thank you for letting me know about the volume issue, Annalise. Let me know if the volume is better now when they speak again. Okay.
So we have a grad student in the audience.
Yes, Annalise, who is in South Africa.
Oh,
Yes, and in fact, she was saying that.
at SALT?
Where are you at, Annalise? And how is that sound? Okay, the volume is fantastic, clear. Okay, excellent. No, Annalise, no, I have it set so that you can't unmute on your end.
Oh yeah, you have to tell us in the chat window.
Yes, please, thank
But if
you.
you tell us in the chat window, we can discuss that way.
That's right. Thank you, Vanya, for that feedback on the volume that's clear and you can hear everyone. Amazing. I appreciate that. Okay, Annalise says, oh yes, it's going fine on your side too. Thank you. Okay, so so Annalise is using test data
Oh yeah.
at present.
That's
Oh
fantastic.
yeah.
Tess actually shot 3i Atlas a couple days ago.
Ah,
Yeah.
nice.
Yeah,
Look at
I heard it almost killed itself though, because in order to observe 3 Atlas, had to look at a weird geometry, and it couldn't get the solar panels pointed in where it's supposed to point, so it almost ran out of power.
Oh, wow.
that. Uh-oh.
What are,
Almost.
what are you? Oh, she sent you a direct message. Oh, okay. What are you? Do you want to tell the audience? Good.
Sorry. Well, we just kind of told everybody that
Yeah, I
she was
guess we
using
just
test
reiterated
data.
that's fine.
So sorry, Annalise.
But Annalise, what are you studying stars or planets or what is your topic with Tess?
And I guess exoplanets probably.
That's what I was thinking because isn't that
That's
what Tess
pretty much
It is an
yeah.
exoplanet machine.
Yeah.
Well, Leo,
Stars, contact
the
by
data here are fantastic. The data
Wow.
here are so good.
Good.
I might only do a box 5 instead of box 9.
Okay,
I think the box 9s are like we'll save those for the really faint stuff.
Okay.
Yeah. But yeah, you can see the object right there. That's it.
oh, that's it?
Wow.
Yeah.
Mm-hmm.
Oh, excellent.
Yeah, it's pretty strong detection.
Yeah, that sticks right out.
Yeah. So I don't think we need to like go full bore here.
Okay,
But yeah, box 5 frames I think is probably good enough.
okay. And I will check the nod amplitudes as well again, just to make sure it doesn't go back to 0.
Okay.
And I've written that up. I think I need to modify the box to their pattern scripts so that it throws you a warning when it's set to 0.
Yeah. It's like, why are you setting it to 0?
Yeah, that might be good to know.
And the thing here, it says box spot 9 pattern, but frame number 98. 1 of 1. So it doesn't show, when we're doing the box 5, it said 1 of 5, 2 of 5, 3 of 5, 4 of 5, or 5 of 5. So we don't know exactly like
Where we are.
yeah, we see if I could scroll up here.
So this is something that I understand, perhaps you and the observers don't, is that it's sort of telling me where it's moving relative to where it was. So you can actually see the offset positions here
Oh yes.
on the facsims.
So it's on position 4 right now.
Yes,
Okay.
so
So this is the 4th image.
yes, so let me show you what that looks like, because we don't have it documented online as well as it should be, but this is the pattern.
Oh, very
1,
nice.
2, 3, 4.
That's perfect. That's beautiful. I guess box 5 is just
Yeah, 5, 6, 7, 8, 9, and I'll show you box 5.
Yep.
So 1, 2, 3, 4, 5.
5 patterns.
Yep.
Look at X. That's pretty cool. All right. So I think we will have to, when it is done with position 5, we will have to do the art of words.
Okay.
Yeah, because I think we want to just do box 5 for the A at H.
I'll set it to a board after frame then.
But this is number 4, I think, right?
Oh, you want it to be after 5?
Yeah, I
Okay,
think.
then I'll wait.
Yeah. So we'll get 5 good ones in there.
Can we ask another question?
Sure.
So we have about 5 questions.
Yeah.
So I'm just kind of
Okay.
waiting. Okay, so.
If I were connected to the Zoom, maybe I could reply in written
No,
or.
you're
Okay.
totally fine. Yeah, no, you're doing the thing. So excited to see you in action, Laura-May. It's great. Okay, so from Vani, and these have been great questions, you all. Thank you, thank you, thank you. So from Vani, are Neptunian Trojans closely related to centaurs, or are they their own unique class of object?
Wow, that's a
Good
great question.
It's a great question, Vani.
So centaurs are objects. So basically TNOs are basically extinct comets. They are comets, but they're just far and away enough from the sun that they're not warm enough that they would start to sublimate their ices on their surfaces and grow a dust tail, like we see with comets closer to the sun. So we call them dormant comets, let's say. Now, centaurs are objects which escaped out of the transit Neptunian disk and are in between the orbit of Jupiter and Neptune. We call those the centaurs. So they're related. They're kind of related. We have similar thing in the inner solar system with near Earth objects and the main belt. Main belt is kind of the source population, and objects escape out of the main belt and go into near Earth object space, and are inhabited the area between the Earth and the main belt. The centaurs are very similar in that respect, but they are transit-Neptunian objects, but ones that escaped the transit-Neptunian belt.
Yes, great question, Bonnie. Thank you, Bryce. Okay.
There's a really great image I'm trying to find that shows the overlap of different categories, like asteroid and dwarf planet, and centaurs and TNOs, and I'm trying to find it.
Yes, please, Laura-May. That'd be great.
Oh no, that's the centaur page for the half man, half.
Not that one.
It's like
Quite.
every now and then when I'm Googling like an M object, just like a galaxy, and it gives me like weapons.
Well, one of the first discovered centaurs was named Chiron.
Oh, Chiron, yeah.
And you know who Chiron is in mythology?
Hmm.
So he is a centaur, half man, half horse looking thing. but he was the teacher of Achilles.
Oh, cool.
Oh,
Yes.
That's cool.
So he taught Achilles how to fight and stuff and shoot bows and arrows and things. So Chiron is a good character.
Shall I send you the link?
oh
of this?
yes, please. Just yeah.
Actually, I can send it to
This
you.
is super special. Laura-May has found something awesome for you all. And while we're waiting for that, we have another question. Question from Vani. What do Neptunian Trojans tell us about the migration path of giant planets?
Oh,
Yeah, that's a great
Great
question.
question, Vani.
So
Okay.
what we are doing with the Neptunian Trojans is we think that they're captured from the trans-Neptunian disk by Neptune. So when Neptune migrated, we see evidence that Neptune was actually much closer to the sun at one point. It was about 20-25 AU from the sun. It's currently an AU is astronomical units. So that is an astronomical unit is one unit of distance, which is that distance which is described as being the distance between the Earth and the sun. So the distance between the Earth and the sun is about 93 million miles. Oh yeah, we have to abort this one. And Neptune is currently at 30 of those, 30 astronomical units. Oh, can you give me a moment? We're going to change filters and such. Oh, it's not listening.
Yeah, it's not
Control C.
listening. Control C didn't work.
Oh no. All right, hold on. We're doing something here.
This is astronomy in real time. No filters, no filters.
Unedited, raw, unfiltered.
Unfiltered. Wait, lots of filters, but yeah, you're right.
Unfiltered. but
Sorry,
filtered.
guys.
No worries. Oh, thank you. Oh, it's just very.
Okay, sorry. It's kind of hard to do this when you do it on the command line.
It doesn't listen.
No, it's not.
Very grumpy.
Right, there you go.
Yes.
Okay. Thank you so much, Leo.
Thank you.
So we're going to go to J band. And you want to change it? It's 10 coordinates. So
Hold on, it's still moving.
but you can change the exposure control.
Yeah.
So integration time is going to be 10 seconds. And you have 18 coordinates. 18. And
J band. Yeah.
yes, J band. And so now hold on, let me do.
Are we still box 9?
No, you
Box
don't.
5.
That's you just hit apply. Just hit apply.
Yeah, and let me check your nods by the way before you do that.
We're good.
Oh, you're in
We're-
J image right now. So the hit apply.
Okay.
So the nods are good.
Yep, nods are good.
Okay, now go there and click on box. Click on the box, and you do box by box. There you go. And now hit enter. We should be good to go. All right. Thank you, Leo.
Welcome.
Thank you, Leo.
Did you get the image I sent to you, Jamaica, by text? I wasn't sure if your text is, or if I can send it to you by email as well. If you
Yeah,
prefer.
no, it should have popped up there. No, I got it. I got it. Thank you, thank you, thank you. Okay, so let me share this.
So the Neptunian Trojans are kind of like a time capsule of the trans-Neptunian disk when Neptune migrated from 20 astronomical units all the way out to 30 astronomical units. When it migrated, it captured these Neptunian Trojans and was placed them in a 1-to-1 mean motion resonance with it. And we think that it kind of is a snapshot of the compositional gradient, the compositional, let's say, a change in composition from inner part of the trans-Neptunian disk to the outer part of the trans-Neptunian disk had a particular pattern with it. And we think that the way that the Neptunian Trojans were captured from the trans-Neptunian disk records what that compositional gradient was. And so what we're doing is we're trying to investigate to try to determine what the compositional types of Neptunian Trojans are, what the bulk compositional properties of the Neptunian Trojan population is like, in order to tell us more about what that compositional gradient in the original trans-Neptunian disk was like.
Yes. Got lots of claps there. Yes. Thank you. Thank you. Thank you. Brilliant. Yes. Yes, your question is next, Bill. Thank you. Thank you all for being so patient with your questions. Okay. So Bill asks, could someone say more about what's possible with MOSFIRE?
Oh, so what we are doing is we're imaging objects between 22nd and 23rd magnitude, which is in the infrared, which is very faint. You're usually trying to, from ground-based telescopes, you're usually observing things much more brighter than that. Usually somewhere brighter than magnitude 20. And so what MOSFIRE is enabling us to do is it's enabling us to see things the very, say, boundaries of the solar system. Another thing that it can do can be used in spectroscopy. It can be used as a spectrograph. So as a spectrograph, it can take observations in the infrared wavelengths, and instead of just getting a single image, which is basically a single data point along an object spectrum, it can get many data points in wavelength along that object spectrum. This MOSFIRE is set up. Its original design was to be a multi-object spectrograph, so it can do spectroscopy of many things, multiple objects all at once. And so if you have a cluster of galaxies that are all in a cluster and next to each other, with MOSFIRE, you can take a spectrum of all those galaxies in one shot, one observation.
All right, Bill, I hope that was a satisfactory answer for you. If you have a follow-up, just place it in the chat. Excellent, excellent. Y'all have great questions. Thank you. Okay. Okay. Yes, we got, thank you for your detailed responses. Yes,
Glad
thank
you like
you.
it.
Yes. Okay.
So we just took the first J-band image, so we'll do the second J-band image. So I think it's better to do things increment of box 5 instead of box 9. If it looks too faint, we just do another box 5. Yeah, box 9 is nice because you get all those dithers. But box 5, I think, is the pattern. Doing 2 box 5s is just as good as doing them.
Yeah, box 9.
Box 9.
It's a nice comet in the southern skies.
Leo, do you know if there's a mode to just do kind of like a random dither?
Not that I'm aware of.
So like what you could do instead of saying nod 20 arc seconds, you could say nod a range like 15 to 25 and do it in the east direction and the north direction. So it gets a random combination between 15 and 25.
There isn't a way to do that currently, but that could be programmed.
And you could give it like a step size. It's random, but a step size of like 2 arc seconds, so that you'll never have stuff like randomly just on top of each other, like switched on top of each other.
Yeah, that's possible, but we don't have a way to do it right now.
Oh, I think
I heard the cat. Yeah.
That's the cat.
That is the cat.
Call it in, Bryce.
Yeah, well, I think the cat liked it. Well, the cat hears our voices, but I think also the food. We had food here last time, and so it could smell the food. But yeah, I think the cat will come out when it feels safe.
Yes, Bill, it is. It is. It's hardware, a MOSFIRE. It's hardware, not just software. Exactly.
Yeah,
exactly.
MOSFIRE. Yes, MOSFIRE is huge. Jamaica saw and I saw MOSFIRE.
Yes.
about a week ago.
That's
It's
right.
like it's pretty ginormous,
Yeah.
and I'd say it's about 8 or 9 feet tall and weighs like 7,000 pounds.
Yeah, it's a spectrograph and detector inside of a very large dewar.
Exactly.
It cools the instrument. What's the temperature? I think it's like 20 Kelvin, maybe.
I saw the detector is 77 Kelvin.
Oh wow,
77 Kelvin.
that's
Wow,
really,
that's yeah, cold. Yeah.
So yeah,
Yeah,
there it
I
is right
think the
there.
rest of the instrument is 120 Kelvin. I could be wrong though. Let me actually check. I can check this right now.
So there's the object right there in J band. It's
Woo,
going north.
nice.
It's making like an elbow right here with this asterisk. Like,
The sky.
yeah, it's going north.
It is.
Yeah, the rest of the instrument is 120 Kelvin inside of the dewar.
Okay. Wow. Cold. Okay. Oh, yes. Okay. Oh, that's right. I did not drop that in the chat. Thanks for reminding me. Small solar system bodies. Okay, let me put that in the chat. And so Laura-May can explain a little bit about this.
Yeah, do you want to talk about that picture she sent over to you?
Yes, please. So if I could type, it would work.
Oh, I
Yes.
gotta do my Duolingo at some point.
Oh wow. Look, no, no. So you know how look it says 657 days since you left me. That's what mine says. What? It's so bad. Okay. So Laura-May, I dropped your
Okay,
link in
yeah.
the chat.
So it's a continuation of what we were talking about earlier. And it's really, it's a Euler diagram. So what it's doing is showing the sets and the relationships. It's a little like a Venn diagram in a way. And so you can see, so we have planets, they're their own separate category. And then we have dwarf planets, minor planets, centaurs, Plutoids. I'm not even sure I know. I guess Plutoids are related to Pluto.
Plutoid.
We've got the TNOs, so those trans-Neptunian objects, comets, the centaurs, the small solar system bodies, and the satellites. And it's funny because it reminds me of the fact that when Ceres was first discovered, so Ceres is a dwarf planet in between Mars and Jupiter, it was originally a planet. Then it got changed to asteroid. It's in fact the dominant, it has something like a large percentage of the mass of the asteroid belt is contained. A third. I thought it was 30%. Yeah. It contains a lot of the asteroid, and it's rounded. It looks like a planet. And so after being demoted to asteroid, it eventually got promoted to dwarf planet. But it is both, I believe it's both an asteroid and a dwarf planet. So some of these categories overlap.
Asteroid and
So you can have some bodies that overlap. And in fact, I think there were some discussions about that regarding Oumuamua, that at first it was unclear if it was comet or if it was
Oh yeah, we
asteroid.
didn't know. We didn't know if it was an asteroid or a comet for a good 4 or 5 months. It's non-gravitational orbital parameters were found for it that suggested it was a comet. So it's basically just so weakly active that you couldn't see any dust, but it was just there was enough mass loss coming from the object that was pushing it.
That's right.
Giving it a push.
Yeah. And you can see on the diagram, some small solar system bodies are also minor planets, but some are also TNOs, but not all TNOs are small solar system bodies. So it's a complicated family in the solar system.
Yes.
And everyone gets to have their own things. And people rage about the dwarf planet categories, but I think they're great. They're all really unique. Some of them are egg-shaped, and there's a dozen of them. They're really cool. And Pluto's in good company.
Yes, very much so. Thank you, Rob, for letting me know that I did not drop that link in the chat to everyone, but now everyone should have a link to it. Yeah.
Good.
Thanks, Rob. Now, wasn't Ceres first asteroid
Yes,
discovered?
yeah.
Okay,
first
it
asteroid
was.
Discovered by the
Yeah.
Italians.
Yeah,
Right?
it was spelled, yeah, his name was Piazza.
That's right.
Piazza.
And he was a monk living in, it was discovered in Palermo,
Palermo,
Sicily.
that's right.
And in 1800, I think it was like 1802. And it was, so he observed it once, and he observed it a couple of times, but then it got lost. And so he was wondering how he could try and recover it, because the Kepler's planetary motion laws were available, were around, they had been invented. So he was wanting to figure out the orbit of this what he thought was a planet at the time. And so he contacted Carl Gauss.
Oh,
So if you heard of Gaussian bell curve,
yes.
and have you heard of chi-square? So Carl Gauss invented chi-square for the purpose of fitting an orbit to the observations that Piazza had taken in order to estimate where the asteroid would be in the future so that it could be recovered. So basically, modern statistics was invented because of asteroids.
Also, there is a great relationship. So I thought it was Giuseppe Piazzi, who discovered Ceres, had an assistant called Nicolaus Cacciatore. And it, it ended up that two stars in the Dolphin constellation, they had very strange names, Rotanev and Swellokin. And no one could figure out where these names came from until it was discovered that if you just reverse the letters, it spells out Nicolaus Cacciatore in the Latinized version of the name. And so it's unclear if Piazzi gave the name to those stars as a tribute to him, or if he put them in. But it was also Palermo Observatory, and it was his assistant. And it's only 2 of 3 stars, I believe, that have proper names, like named after a person.
Yeah.
The rest of the stars, have names, and Betelgeuse that corresponds to, I think it means shoulder, I think, or they have all sorts of interesting names like that.
Not to be confused with Betelgeuse.
I know you guys say Beetlejuice. I don't like it. It's called Betelgeuse.
Well, in the original, so in the original movie, Betelgeuse,
Was
by
that
Tim
movie
Burton,
even named
they-
after the star?
no, well, so on the title it's called Beetlejuice.
Yes.
But
Right.
if you look, if you watch the original movie by Tim Burton, and what was the guy's name? He was also Batman. The actor's name who plays Beetlejuice.
Oh my gosh.
Yeah.
Michael Keaton.
Michael Keaton.
Oh,
Michael
yeah,
Keaton plays
right.
Beetlejuice. So if you watch the movie, he's actually called Betelgeuse. He's named after the star.
Oh, okay. So why did they change the title to Beetlejuice?
Probably to make it more pronounceable.
So he's named. Okay, so he is named after the star.
He is named after the star.
I did not remember that.
Well, in French, it's called Betelgeuse. Okay.
Oh, it just sounds better in French anyway.
I respect the language that it keeps.
Okay.
There.
Yeah.
I didn't know that it's moving.
So we look at the
Orientation.
ephemeris. So look, I'll show you a movie. Watch this. So this is the Arian deck from 45 minutes ago.
Oh.
So I'm gonna copy and paste it in here, and watch. So you see it go down. So now I'm gonna put it from where it is now.
And then did you pre-calculate those values, or is
Yeah.
that from something?
That is the Minor Planet Center and JPL Horizons. Yeah. In H, it's very, very messy. H is the worst in terms of the atmospheric opacity and background. But we're going to do our best here. And when we get our second H frame, we will hope to see the asteroid.
What are those streaks?
Yeah, it's kind of the flat field. But I'll stay on Zoom in case the cat decides to come in. But that's just the way cats are, they do their own thing. They do what they
They're
want.
just like comets.
Yeah.
They do whatever they want.
Yes.
I'd say comets are like cats.
Yeah.
Just so
There.
in the cat. Someone recognized you from All Space Considered. Yes, Miss Yulee, this is Laura-May, who is the host at the Griffith Observatory for All Space Considered. Yes, you're absolutely right. Yes, yes,
Oh,
yes.
Fancy.
And
Gosh.
oh, we should talk about the founder of Shadow the Scientist is actually this month's
Yes.
guest.
Yes, Raja is going to be on All Space Considered this month, and we have a special episode. We're doing a double AS episode. We want to make it like immersive and bring you into what is the double AS. The double AS is our Super Bowl of astronomy, appropriate for this weekend. But we all gather in a different city every year, and we get to have a lot of talks, a lot of exchanges. There's little booths where you can get every item of merch in the world. And so we're doing a very special episode for it. Raja was one of the plenary speakers. So that's basically one of the people who gave one of the big main talks in the main hall. And so this is going to be a very exciting episode. Last year we did a fake awards ceremony for lots of different science that came out of the AAS, and we gave it, but oh no, we did a tier list rating. We did a tier list rating, and then we gave them awards, you know, like bronze, silver, and gold. This year, no more award ceremony, but an immersive experience. So I hope it'll be fun.
Ooh, yes. I'm looking forward to it. Yes. Let me put a link
And thank you
to.
for watching All Space. We appreciate you.
Absolutely. Let me put a link to All Space Considered. And let me put that in the chat. Yes.
so
Oh
here's
my
the
God.
asteroid in H-band. That's it right there. It's not as bright, but it's there. That's it.
One more question that I didn't get to, but I don't know where it is in there, but the question was about the Neptunian Trojans. What is causing them to be red? And how does that change between some of the other asteroids? Because some are redder than others. And I had shared your Earth and Sky article about
thank you.
the reddening,
Oh, yeah.
Neptunian Trojans. Yes.
Yeah, so we think the redness is related to that some have methanols on them and some have purely just water ice on them. Water ice is more blue, but the methanol and other complex organic molecules are very red. So if you look at pictures of Pluto, it actually has like a very parts on it that are ultra red. We call it ultra red matter. We call it red matter, ultra red matter, and we think that that is what's responsible for a lot of the Kuiper Belt objects having a very red appearance.
Excellent. Thank you for that. Thank you. Thank you. That was a great way to round things out. And we have so many thank yous from Bill. It was great to join you. Thanks for doing this. Thanks for a great session from Annalise. Thanks for the session from Rob. Thank you, Rob. Mark, thank you. Thank you. And he says thank you too. And from Vonnie, such a fun, entertaining, and informative session. Yes, yes, yes. Amazing. Thank you all for being with us. Tomorrow night, we're right back here continuing their investigation.
Thank you, Jamaica, also. Sorry I interrupted you, but for the amazing hosting and for our beautiful
thank you for
plays.
Yeah.
Our amazing host, as always. Jamaica.
I'm so grateful.
Leo, of course. And Eva isn't here, but I think she's just like random there.
Yes, and Leo.
He's hanging out.
Absolutely. And of course, at the summit, Heather.
Thank you, Heather.
Yes, Heather, and you're so patient and indulgent of us. We appreciate you.
Understanding.
Yes, very much so.